A linked list is a dynamic data structure that is made up of nodes arranged in sequential form. Dynamic data structure means that we can allocate the required memory while the program is running. So a dynamic data structure can expand or shrink easily during runtime. Unlike arrays, data in a linked list is not stored in contiguous memory locations. When compared to arrays, insertion and deletion of elements is easier in linked lists, as there is no need to reallocate or reorganize the whole list structure. In arrays, insertion and deletion involves shifting of elements, while in linked lists, there is no physical movement of data while inserting or deleting elements. We can use linked lists to implement abstract data types like lists, stacks, or queues. Now, two disadvantages of linked lists are that efficient random access is not possible and some extra memory is required for the implementation. There are different variants of linked lists. In this course, we'll study about these four variants, out of which the single linked list is the simplest one. So we'll start with single linked lists. A single linked list is made up of nodes where each node has two parts, the info part and the link part. The info part contains the actual data that has to be stored in the list, and this link part is a reference to the next node of the list. This is an example of a single linked list with four nodes. The info part contains an integer value. This can be of any other type also. The link part of each node is a reference to the next node. So the link part of this node refers to this node. Link part of this node refers to this node. Link part of this node refers to this node. Now this is the last node, so its link part is null. We maintain a spatial reference variable that always refers to the first node of the list. We have named it start. This reference is the identity of the list, and with the help of this reference only, we can access all the elements of the list. For an empty list, this start will be null. Now let's see how we can implement a single linked list. This is a class node that represents a node of a single linked list. This variable info represents the actual data that has to be stored in the list. We have taken it to be of type int. It can be of any other type also. This link is of type node and it always refers to the next node of the list. This is the one argument constructor. Info is initialized with I and link is initialized to null. This is a single linked list class. Here we have this variable start, which always refers to the first node of the list. In this constructor, we have initialized this start to null. In the next few lectures, we'll develop all these methods of the single linked list class. In this class demo, we have this main function in which we test the single linked list class. Here we have created a new single linked list object. With the help of this method create list, we create a single linked list, and then inside this while loop, we'll perform all the operations on the list with the help of all these methods. So in the next few lectures, we'll see how to develop and test all the methods of the single linked list class. In this video, we'll see how to traverse a linked list. Traversal means visiting each node exactly once. So we'll start from the first node and visit each node till the last node. Before studying traversal, let us see how we can move a reference forward in a linked list. Suppose we have a reference P that refers to this node and we write this statement P equal to P-link. Now P-link refers to this node. So if we assign P-link to P, then P starts referring to this node. So writing this statement P equal to P-link makes P refer to the next node of the list. Now we'll see how we can traverse our linked list. We have to start from the first node. So we'll take a reference P that refers to the first node. To make P refer to the first node, we'll initialize it with start because start refers to the first node. Now while visiting each node, we'll print the contents of the node. P refers to this node, so P info is 10, so 10 is printed. We write P equal to P link, so P now refers to this node. Now P info is 20, so 20 is printed. Again we write P equal to P link. So P now refers to this node. And now P info is 30. So 30 is printed. Now P refers to this node. 40 will be printed. Now P refers to this node. So 50 will be printed. Now when we write P equal to P link, P will become null. And so we can stop because we have reached the end of the list. We can see that we are repeating the same statements again and again. So we can write this in a loop. And the terminating condition for that loop would be when P becomes null. So this is the loop. P is initialized with start. And this loop continues till P is not null. In each iteration of this loop, we are printing the value of P info and we are moving this P forward. So this is how we can traverse a list starting from the first node till the last node. We can use the same loop for counting the number of nodes in the list. Here we have taken a variable n, initialized it to 0, and whenever we are visiting a node, we are incrementing this n. So when this loop terminates, this value of n will give us the number of nodes in the list. Now we'll see how we can use this loop to search for an element in the list. Suppose we have to search for an element x in the list. Now whenever we visit a node, we check the info of that node. And if the info of that node is equal to x, then this break is executed and we come out of the loop. We have taken this variable position and initialized it to 1. We increment it each time a node is visited. So when this loop terminates and x is found, the value of this variable position will give us the position of the node that contains value x. Now this loop can terminate in two conditions. One when element x is found and break is executed, and one when x is not present in the list and we reach the end of the list and P becomes null. So after this loop terminates, if P is null, it will mean that x is not present in the list. Otherwise, value of this variable position will give us the position of the node that contains x. This is the display list method which displays all the elements of the list. If the list is empty, then we'll just print this message and return. Otherwise, we'll display all the elements of the list starting from the first element till the last element. This count nodes method displays the number of nodes in the list. If you want, you can return the value of this n from this method. This method search will return true if element x is present in the list. Otherwise, it will return false. In our main, we have called these methods display list, count nodes and search in cases 1, 2 and 3. Now let's run this program. Now this display list displays the list. Number of nodes in the list is equal to 5. We search for an element. 3 is present at position 3. 56 is not found in the list. Before studying insertion in a linked list, let's see how we can move in a linked list and find references to some particular nodes. In this video, we'll see how to find reference to the last node of the list, reference to second last node, reference to a node with a particular info, reference to predecessor of a node with particular info, and reference to a node at a particular position. So first, let's see how we can find reference to the last node of the list. This is the last node, so we need a reference to this node. This is the code that will give us reference to the last node of the list. While traversing the list, we had seen that the loop condition was P is not equal to null. So there the loop stopped when P became null. Now here the loop condition is P link is not equal to null. So here the loop will stop when P link becomes null. And P link will become null when P refers to the last node of the list. Because link part of last node is null. So when this loop stops, P will refer to the last node of the list. So this is how we can find reference to the last node of the list. Now let's see how we can find reference to the second last node of the list. This is the second last node, so we need a reference to this node. This is the code that will give us reference to the second last node. Now here the loop condition is P link link is not equal to null. So this loop will stop when p link becomes equal to null, and p link will become equal to null when p will refer to the second last node of the list. Because when p refers to the second last node of the list, p link will refer to this last node and p link will be null. So when this loop stops, p will refer to the second last node of the list. Now we'll see how we can find reference to a node with a particular info. Suppose we are given this value x and we have to find reference to a node that contains this value x. If the value of x is 30, then in this list we have to find reference to this node. This is the code that will give us reference to a node that contains value x. We have already seen this code while we were learning searching in a linked list. So this loop will stop when p refers to the node that contains x. And if x is not present in the list, then p will be null. Now we'll see how we can find reference to predecessor of a node with particular info. Suppose we are given this value x and we have to find reference to predecessor of the node that contains x. If value of x is 30, then in this list we have to find reference to this node, because this is the node that contains 30 and this is the predecessor of this node. This is the code that will give us reference to predecessor of the node that contains x. Here inside the loop we are checking p link info instead of p info, and the loop condition here is p link is not equal to null. So this loop will stop when p refers to the last node, because when p refers to the last node, we don't want these statements to work. Now let's see how this code works. Initially p refers to the first node of the list. Now p link is not equal to null, so we check p link info. P link info is 20, it is not equal to x. So break is not executed and p is moved forward. Now p link is not equal to null, so again we check p link info. Now p link info is 30, so p link info is equal to x. So now this break statement is executed and this loop terminates. So we can see that when this loop terminates, p refers to the node that is the predecessor of the node that contains value x. Now let's see how we can find reference to a node at a particular position. These are the positions of the nodes in this list. Suppose we are given a value k and we have to find reference to a node that is at kth position in the list. So if the value of k is 3, then in this list we have to find reference to this node. This is the code that will give us reference to the kth node of the list. Let's see how this code works. Initially p refers to the first node and I is equal to 1. Now I is less than k and p is not equal to null, so p is moved forward and I is incremented. Now again I is less than k and p is not equal to null, so p is moved forward and I is incremented. Now I is not less than k, so this loop terminates. So we can see that when this loop terminates, p refers to the node that is at kth position in the list. This condition p is not equal to null we have placed to terminate the loop in the case when there is no kth position in the list. That is, the number of nodes is less than k. For example, if k is 10 and there are only 5 nodes in the list, then this condition p is not equal to null will terminate this loop. In this video, we'll see how we can insert a new node in a single linked list. These are the different cases of insertion. We'll see all the cases one by one. To insert a new node, we'll allocate a node and make this reference temp refer to that node. This is the node class constructor. So this data will be used to initialize the info part and the link part will be initialized to null. Now first let's see how we can insert a new node in the beginning of the list. We allocate a new node, make this reference temp refer to this node. Now after insertion, this node will be the first node. So start should refer to this node and this node will become the second node of the list. So the link of this node should refer to this node. So first we make link of this node refer to this node. We write temp link is equal to start because this node is referred by start. Next we change start and make it refer to this node. So we write start is equal to temp. So these are the two statements that we need to write for inserting a new node in the beginning of the list. Now the order of these two statements is important. Let's see what happens if we change their order. Now first we write start is equal to temp. So start refers to this node. Now we can see that the link to this part of the list is broken. And now if we write temp link is equal to start, this node will refer to itself. And whenever we process the linked list, we'll be stuck in an infinite loop. So this is the correct way of inserting a new node in the beginning of the list. Now let's see how we can insert a new node in an empty list. For an empty list, start is null. We allocate this new node. Now this node will be the first node of the list. So start should refer to this node. So we just have to write start is equal to temp and this new node will be inserted in the empty list. Now let's see how we can insert a new node at the end of the list. For this we need a reference to the last node of the list. We've already seen how we can find reference to the last node of the list. After finding this reference, we allocate this new node. Now link part of this node should refer to this node. So we write plink is equal to temp and so this new node is inserted at the end of the list. Now let's see the code for all these insertions in our program. This is the method for inserting a new node in the beginning of the list. Here we are allocating a new node. Then we are writing temp link equal to start and start equal to temp. This method will also work properly when we have to insert in an empty list. Because for an empty list, start will be null. So we'll have temp link equal to null and start equal to temp. This is the method for inserting a new node at the end of the list. If the list is empty, then we'll just write start equal to temp and return. Otherwise, we'll find reference to the last node of the list. And then we'll write plink equal to temp. But this p is a reference to the last node of the list. In this create list method, we'll create a new list. Here we are entering the number of nodes. And here we are inserting all the nodes with the help of this method insert at end. This method create list we have called here in the beginning of the program. We are inserting in the beginning in option 4 and we are inserting at the end in option 5. So we have called this method insert in beginning in case 4 and we have called this method insert at end in case 5. Now let's run this program. First we'll create a new list. This is our list. Now we'll insert in the beginning of the list. So this 55 was inserted in the beginning of the list. Now we'll insert a new node at the end of the list. So this 99 is inserted at the end of the list. Now we'll see how we can insert a new node between two nodes of a list. Suppose we have to insert a new node between these two nodes. For that we'll need a reference to this node. We allocate a new node. Now for this node to come in between these two nodes, the link part of this node should refer to this node and the link part of this node should refer to this node. So first we'll make link part of this node refer to this node. We'll write temp link is equal to plink and then we'll make link part of this node refer to this node. So we'll write plink is equal to temp. So these are the two statements that we need to write to insert this new node in between these two nodes. Now the order of these two statements is important. Let's see what happens if we change their order. Suppose first we write plink is equal to temp. We can see that the link to this part of the list is broken. And now if we write temp link is equal to plink, then this node will start referring to itself. So this is the correct way to insert a new node in between two nodes of the list. Now we'll see how we can insert a new node after a given node, how we can insert a new node before a given node, and how we can insert a new node at a given position. These two statements of insertion will be the same in all three cases. The only difference will be in how we find this reference P. First, let's see how we can insert a new node after a given node. Suppose we are given a value x and we have to insert a new node after the node that contains x. If x is 56, then in this list we have to insert a new node after this node. That means we have to insert a new node between these two nodes. And for that we need a reference to this node. We've already seen how we can find a reference to a node that contains value x. After finding this reference, we'll allocate a new node and insert it here in between these two nodes by writing these two statements of insertion. So this is how we can insert a new node after a given node. Now let's see how we can insert a new node before a given node. Suppose we are given this value x and we have to insert a new node before the node that contains x. If x is 45, then in this list we have to insert a new node before this node. That means we have to insert a new node between these two nodes. And for that we need a reference to this node. So if we have to insert a new node before a node that has value x, we need a reference to the predecessor of the node that contains x. We have already seen how we can find this reference. This code will give us a reference to the predecessor of the node that contains x. After finding this reference, we allocate a new node and insert it here, writing these two statements of insertion. Now let's see how we can insert at a given position in a list. Suppose we are given a value k and we have to insert a new node at kth position in the list. If value of k is 4, then in this list we have to insert a new node here. The position of the new node will be 4, position of this node will become 5 and position of this node will become 6. So that means we have to insert a new node between these two nodes, and for that we require a reference to this node. So if we have to insert a new node at kth position in the list, we require a reference to k minus 1th node of the list. We have already seen how to find this reference. This code will give us reference to k minus 1th node of the list. After finding this reference, we allocate a new node and insert it here using these two statements of insertion. So now this new node becomes the 4th node and this becomes the 5th node and this becomes the 6th node. Now let's see the methods insert after, insert before and insert at position. This is the method insert after, which will insert a new node after the node that contains value x. So here first we find reference to the node that contains x. After this loop terminates, if p is null, it means that x is not present in the list. Otherwise, p will refer to the node that contains x, and in that case, we'll allocate a new node and insert it by writing these two statements. This is the method insert before, which will insert a new node before the node that contains value x. And we have seen that in this case, we need reference to predecessor of the node that contains x. After finding this reference, we'll allocate a new node and insert it by writing these two statements. Now before doing this, we have put two checks here. If the list is empty, in that case start will be null and we'll just return, because in that case we don't want this code to execute, because p will be null and accessing p link will give us error. Now if x is present in the first node, then we have to insert the new node in the beginning of the list, and in that case start has to be updated. So this case also we have handled separately. Now let's see the function insert at position. This method will insert a new node at kth position in the list. And in this case, we have to find reference to k minus 1th node of the list. After finding this reference, we allocate a new node and insert it by writing these two statements. If the node has to be inserted at first position, in that case, start has to be updated. So this case we have handled separately. Now let's run this program. This is our initial list. Now we'll insert a new node after node 3. So this new node is inserted after node 3. Now we'll insert a new node before node 4. So this new node is inserted before node 4. Now we'll insert a new node at position 4. So this new node is inserted at position 4. Now we'll try to insert a node at position 15. So it is showing that you can insert only up to 9th position. In this video, we'll see how to delete a node from a single linked list. These are the different cases that we'll see. Deletion of first node, deletion of the only node, deletion in between the list, and deletion at the end. First, let's see how we can delete the first node of the list. Now, after deletion, this node will become the first node of the list. So, start should refer to this node. So, we'll just write start is equal to start link. And now, this node will not be a part of the list. To delete the only node of the list, we'll just write start is equal to null, and this node will not be a part of the list and the list will become empty. Now let's see how we can delete a node that is in between the list nodes. Suppose we have to delete this node from the list. For that we need a reference to the predecessor node. So we need a reference to this node. Now for deletion of this node, the link part of this node should refer to this node. So we'll just write plink is equal to plink link. So now this node is not a part of the list. Now to delete the last node of the list, we need a reference to the second last node. So we'll just write plink is equal to null. So now this is the last node of the list and this node is not a part of the list now. Now let's see the methods delete first node, delete last node and delete node. This is the method delete first node which will delete the first node of the list. If the list is empty, we'll just return. Otherwise, we'll write start is equal to start link. This is the method delete last node. It will delete the last node of the list. If the list is empty, we'll just return. If the list has only one node, then we'll make start equal to null and return. Otherwise, we'll find reference to the second last node of the list. So after this loop terminates, P will refer to the second last node of the list and we'll write plink is equal to null and it will delete the last node of the list. Now this is the method delete node which will delete a node that contains value x. If the list is empty, we'll just return. If x is present in the first node, that means we have to delete the first node. We'll write start equal to start link and we'll return. Otherwise, we'll find reference to predecessor of the node that contains x. And then we'll delete the node that contains x by writing plink is equal to plink link. Now let's run this program. This is our initial list. We delete the first node of the list. The first node is deleted. Now we delete last node of the list. The last node is deleted. Now we delete node 3 from the list. Node 3 is deleted.